Hello students, welcome to Sri Siddheshwar Women's College of Engineering Solapur. We are dealing with the unit of functions of complex variable differential calculus part. So far we have studied the concept of analytic functions. Now we are going to discuss the concept of harmonic functions. So let us see the definition of harmonic functions. Any function of xy which has continuous first and second order partial derivatives and which satisfies Laplace equation dou 2 phi by dou x square plus dou 2 phi by dou y square equal to 0 is called a harmonic function. Or in polar form, any function of r and theta which has continuous partial derivatives of first and second order and which satisfies Laplace equation dou 2u by dou r square plus 1 upon r dou u by dou r plus 1 upon r square dou 2u by dou theta square equal to 0 is called a harmonic function. Let us see one example. Verify that the real and imaginary parts of f of z equal to e raised to z are harmonic functions. So first we have to write the function f of z equal to e raised to z. Now to find the real and imaginary parts, replace z by x plus iy, applying laws of indices and writing e raised to iy as cos y plus I sin y, we get real part u is equal to e raised to x into cos y and imaginary part v is equal to e raised to x sin y. Now consider the real part u, find its two first order partial derivatives and then second order partial derivatives with respect to x and y. Now from these results it is clear that adding these results you will get the answer as 0, that is dou 2u by dou x square plus dou 2u by dou y square equal to 0, means the real part u satisfies Laplace equation and hence the real part of f of z is a harmonic function. In the same way you can prove that the imaginary part v of xy equal to e raised to x sin y is a harmonic function. So from the two second order partial derivatives it is clear that their sum is 0, that is function v is satisfying Laplace equation and hence imaginary part of f of z is a harmonic function. Now we will see to form the analytic function when its real part is harmonic function and it is given to you. So the procedure is very similar to the formation of analytic function f of z equal to u plus iv when its real part u is given. So this is your required analytic function f of z. You are given u, find ux and uy, call them as phi 1, phi 2. Apply Milne-Thomson method with the formula f dash of z equal to phi 1 of z0 minus I times phi 2 of z0. You will get f dash of z in terms of z. Integrating you will get the required analytic function in terms of z. Let us see one example. Here function u is given to you. It is an algebraic function. We have to show that this function u is a harmonic function and also we have to find its harmonic conjugate. Let us see the solution. So to prove that the function is harmonic function, you should have two second order partial derivatives of this function u with respect to x and y. Find first order partial derivatives and then find second order partial derivatives dou 2u by dou x square and dou 2u by dou y square. Adding these two results we get the answer 0. So it shows that function u satisfies Laplace equation and hence it is a harmonic function. Now we have to find its harmonic conjugate and for that we require its corresponding analytic function f of z equal to u plus iv. So for that we are going to apply Milne-Thomson method. We are having the results for ux and uy. We call them as phi 1 and phi 2 to apply Milne-Thomson method. So write the corresponding formula for f dash of z. In phi 1 and phi 2 results, replace x by z and y by 0. With this we get f dash of z as 4z minus I into 3z square. So f dash of z is a function of z only. Integrating both the sides with respect to z, we get f of z is equal to 2z square minus I z cube plus c. So this is the corresponding analytic function of the given u function. But this is not the final answer. We have to find the harmonic conjugate, that is function v of the given function u. So for that, in this result of f of z, replace z by x plus iy, perform the required calculations, that is square expansion of x plus iy and cube expansion of x plus iy, simplify and collect the real terms and imaginary terms separately. So with this we get the harmonic conjugate of the given function u as v function, that is the imaginary part of this f of z, as 4xy minus x cube plus 3xy square. So this is the harmonic conjugate of the given u function. Now second method, to form the analytic functions if the imaginary part v is given as a harmonic function. So the procedure is very similar to find the analytic function f of z when its imaginary part is given. So find vy and vx, call them as psi1 and psi2. Apply Milne-Thomson method with the formula f dash of z equal to psi1 of z comma 0 plus I times psi2 of z comma 0. Integrate both the sides with respect to z, you will get the required analytic function. Let us see one example to apply this procedure. Here you are given function v as e raised to x into sin y. First part is we have to show that this is a harmonic function, and then we have to find its harmonic conjugate. So let us start the solution. So this is our required analytic function. Function v is given to you. Find its first order partial derivatives and second order partial derivatives. Adding the two second order partial derivative results, we get 0. That is, function v satisfies Laplace equation, and hence function v is a harmonic function. So this is one part of the solution. Now to find its harmonic conjugate, first we have to find its corresponding analytic function using Milne-Thomson method. So applying Milne-Thomson method and writing psi1 and psi2 in terms of z and 0, replacing x by z and y by 0, we get f dash of z is equal to e raised to z simply. Integrating, we get f of z is equal to e raised to z plus c. But this is not a final answer. This is just the required analytic function of the given u function. Now to find the harmonic conjugate, replace z by x plus iy. Applying laws of indices and writing e raised to iy in terms of cos y plus I sin y, we get the harmonic conjugate as u equal to e raised to x cos y. As here the imaginary part is given, so its harmonic conjugate will be the real part of the obtained analytic function f of z. So in this way you can form the analytic function if its corresponding real or imaginary part is given as a harmonic function. So with this we conclude this video lecture. Have a nice time.